So in this video, let us look at a very important topic, which is allied angles or positions. So now once you understand the definitions of the trigonometric ratios, so we have seen that sine theta is nothing but once you rotate the ray through an angle theta, you take a point on that ray which is x comma y, and if r is the distance to that point from origin, sine theta is defined as y coordinate by r, cos theta is x coordinate by r, and tan theta is y by x, y coordinate by x coordinate. This is the definition. Now, so let us take a position of a ray. So let us say that the ray is making an angle of theta with x-axis. Now let px comma y be a point on this ray. Now corresponding to this point, you can find the images of this point about x-axis, that will be x comma minus y, about y-axis, that will be minus x comma minus y, and about the origin, which will be equal to minus x and minus y. So you can very clearly see that this forms a rectangle. Now corresponding to this position of the ray, the values of trigonometric ratios are y by r, x by r, and y by x. Now what are the trigonometric ratios corresponding to this position? Corresponding to this position, because this is a rectangle, all these lengths will be same, all these lengths will be r. So corresponding to this position, sine theta is equal to y by r, cos theta is equal to minus x by r, tan theta is equal to minus y by x. And corresponding to this position, sine theta is equal to minus y by r, cos theta is equal to minus x by r, and tan theta is equal to minus of y by minus x, that is plus y by x. And corresponding to this position of the ray, the values of sine theta is minus y by r, cos theta is plus x by r, tan theta is minus y by x. So what I want you to observe is the values of sine theta correspond to this position, this position, this position, and this position are all magnitude wise same. That is, modulus of sine theta correspond to all these positions is same. So correspond to all these positions, mod sine theta is some constant. Only the sign changes. Depending on the quadrant, the sign changes, but magnitude wise all are same. That is, if I say that this angle is such that sine theta is 0.4, for this position also magnitude of sine theta will be 0.4. For this position also magnitude of sine theta is 0.4. For this position also magnitude of sine theta is 0.4. Depending on the quadrant, you can decide the sign afterwards. The number is very easy to find. The sign can be found using the quadrant in which it lies. Similarly, modulus of cos theta is also equal, because cos theta is x by r, minus x by r, minus x by r, and x by r. So magnitude wise, if you take away the sign, the number is same. Similarly, the case with tan theta. So these four positions are called allied positions. So if you take a certain position theta, 180 minus theta, so if this is theta, this is also equal to theta. So this angle will be 180 minus theta. This angle will be 180 plus theta, and this angle will be 360 minus theta. So if I take the positions theta, 180 minus theta, 180 plus theta, and 360 minus theta, so and this can go on, 360 plus theta, you get the same position, 360 plus theta, and this angle will be 540 minus theta, 540 degrees plus theta. So all these positions are called allied positions. All these positions are allied positions because the trigonometric ratios correspond to all the four positions will be numerically same. And what is the conclusion that you can do from this concept? That means if you know the trigonometric ratios for the angles in the first quadrant corresponding to the angles in the first quadrant, all these angles are allied angles to the angles in the first quadrant. So if you take angle in any quadrant, if you want the trigonometric ratio correspond to angle in any quadrant, you'll get some allied position in the first quadrant. So if I want sine of this angle, I don't need to find sine of this angle. I can go to sine of this angle, the allied angle. I'll get the number, and depending on the quadrant, I'll just put the sign before it. So this allied position concept is a very important concept. So from this, the conclusion is that whatever angle, if you want the trigonometric ratios for any angle, so you can slowly bring that angle to the first quadrant and then find the number, and then depending on the quadrant, you can decide the sign of it. So let us take an example. So we have already seen that in the first quadrant, I know the trigonometric ratios of certain angles: 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. So these are some standard angles for which I know the values of trigonometric ratios. So now let us say that I want to find sine of 120 degrees. Sine of 120 degrees. So how do I do it? So first, I'll rotate the ray through an angle of 120 degrees. So we know that the ray stops somewhere in the second quadrant. Now I don't know actually the value of trigonometric ratios for angles in the second quadrant. So standard angles, I know the trigonometric ratios for angles only in the first quadrant. So how do I find sine 20? So I can use the concept of allied positions. So now this angle is 120 degrees. So now let us find the allied position of this in the first quadrant. Allied position is nothing but the mirror image position, right? So if I take the mirror image of this point about y-axis, you can very clearly see that this angle will be 30 degrees. So this angle will also be equal to 30 degrees. So this angle will be 60 degrees, right? So 120 degrees is allied with 60 degrees. That is, the trigonometric ratios for 60 degrees and 120 degrees are magnitude-wise same. So sine 120 magnitude-wise, it is same as sine 60 degrees magnitude-wise. But sine 60 in the first quadrant, all the trigonometric ratios are positive. So to find sine 120, the sine of sine 120, we just need to go for the quadrant. So 120 degrees is in the second quadrant. So sine of an angle in the second quadrant is positive. All sine, tan, cos, right? So sine in second quadrant is positive. So this remains positive. So the answer is plus root 3 by 2. So sine 120 degrees is plus root 3 by 2. So now let us try to find tan of 300 degrees. So if you want tan of 300 degrees. So just rotate the ray through 300 degrees. So we know that it is 90, 180, 270 and 300 lies somewhere here. So this angle is 300 degrees. So if you want tan of 300 degrees, so calculate the allied position of this. So if this is 300, we know that this is 60 degrees. This angle is 60 degrees. Now if you take the mirror image, of this on the first quadrant, so you get the same position, right? So you get the exactly same position. 60 degrees, if you take the mirror on x-axis, it is plus 60 degrees. So now for 300 degrees also, the allied position in the first quadrant is 60 degrees. So tan 300 degrees is magnitude wise equal to tan 60 degrees. Now let us go for the sign of it. Is it positive or negative? So 300 degrees lies in the fourth quadrant. So tan 300 has to be negative. But tan 60 degrees is positive. So you put a negative sign here. So tan 300 degrees is minus root 3. So I hope you have understood the power of this understanding of allied positions. So next you need to understand the allied positions of type 2. So there are two types of allied positions. The allied positions which you have already studied, that is type 1. Now the type 2 allied positions. So if you have a point P and this position makes an angle of theta with x-axis. So let us consider a similar position of the ray such that the ray makes an angle theta with y-axis. So if this point is x comma y, this point will automatically be equal to y comma x, right? Because you get the same triangle here. So you have a horizontal triangle, you have a vertical triangle. So this will become equal to this. This will become equal to this. So x comma y becomes y comma x. So if this is theta, this position is nothing but 90 minus theta, right? 90 minus theta. So these two positions are called anti-allied positions. These two are also allied, but not in a straightforward way. This is anti-allied positions. So anti-allied positions. So what is the nature of the trigonometric ratios correspond to these two positions? So as you can see, the sine theta is nothing but y by r, right? And sine of 90 minus theta correspond to this position. Now the y coordinate has become x by r. So the sine of this angle will be equal to the cos of this angle, and cos of theta, which is equal to x by r, is equal to cos of 90 minus theta, which is y by r, right? So cos of this angle will be equal to sine of this angle. Sine of this angle will be equal to cos of the other angle. So when you go from one position to its anti-allied position, sine becomes cosine, tan becomes cot, secant becomes cosecant. So the ratio goes from the normal trigonometric ratio to its co-trigonometric ratio. So if it is a co, the co will be removed. So there are four anti-allied positions correspond to theta. So this is theta, let this be the original position. The anti-allied positions are 90 minus theta, and the mirror images of this. The allied positions of all these angles are anti-allied positions to this angle. So theta, 90 minus theta correspond to theta, 90 minus theta, 90 plus theta, 270 minus theta, 270 plus theta, so on. 450 minus theta, 450 plus theta, so on, are called anti-allied positions to theta. What are the allied positions of theta? Which are 180 minus theta, 180 plus theta, 360 plus theta, 360 minus theta, so on, are allied positions. These positions are called anti-allied positions. So if you see clearly, the anti-allied positions are related to odd multiples of 90 degrees. The allied positions are related to even multiples of 90 degrees. And if you go to anti-allied positions, the sine of the original angle will be equal to the cosine of the anti-allied position. Tan will become cot, cosecant will become secant, so on. The trigonometric ratio will change as you go from this angle to this angle.